Hello everyone, welcome to Neso Academy. We are learning theory of computation, and in the previous lecture, we have understood how to construct Mealy machines. And now in this lecture, that is construction of Moore machines, we will understand how to construct Moore machines. So the topic for this lecture is construction of Moore machines. Let's get started with our very first problem. Construct a Moore machine that prints A whenever the sequence 10 is encountered in the input string, otherwise prints B. So in this question, you are required to construct a Moore machine that will generate the output symbol A whenever the sequence 10 is detected in our input string, and otherwise it will generate the output symbol B. Now this question I have already explained you in the previous lecture. In the previous lecture, we have constructed the Mealy machine for the same problem. And now we are required to construct the Moore machine for this problem. So obviously, we will start with the construction of DFA for accepting the strings ending with the sequence 10. So here is the required DFA. And as you can see, as per this DFA, it will accept only those strings that are ending with the sequence 10. And now we are required to convert this DFA into its corresponding Moore machine. As Moore machine is also a finite state machine with output, so there is no requirement of final state. So we will remove the final state. And now we need to associate the output symbol with all the states. In case of Mealy machines, the output symbols are written along with the input symbols over the transitions. But in case of Moore machines, the output symbols are written along with the states. Now, as per the question, you have to construct the Moore machine that will print the output symbol A whenever the sequence 10 is detected. So when the sequence 10 is detected, then only the output is A. That means the sequence 10 is detected after reaching the state Q2. So on the state Q2, we will write the output symbol A, because at the state Q2, we are getting the sequence 10 as per the question. And otherwise, we have to print B. That means in all the other states, the output symbol will be B. So for the state Q0, output symbol will be B. And for the state Q1 also, the output symbol will be B. So this is the required Moore machine for the given problem. I hope you all have understood how to construct a Moore machine for detecting the sequence 10. Now we will proceed with our second problem. Construct a Moore machine that produces the ones complement of any binary input string. That means you are required to construct a Moore machine that will produce the ones complement of any binary input string. Now, ones complement means if the input symbol is 0, the output symbol will be 1. And if the input symbol is 1, then the output symbol will be 0. Basically, we have to flip the bits. 0 becomes 1 and 1 becomes 0. That is ones complement. And in this question, you are required to construct the Moore machine to calculate the ones complement of any binary number. So let's start with the initial state, that is Q0. And you can see here, the initial state Q0 is associated with the output symbol hash. Now, as per this question, we need to calculate the ones complement. So the input symbols and the output symbols can be 0 or 1. Then why I have used hash as an output symbol? I have explained you. In case of Moore machine, if the input is of length n, then the output is of length n plus 1. That means without even reading an input symbol, one output symbol will be generated. That will be of no use. Now, if I use 0 or 1 in place of this hash, then it will make the ones complement incorrect, because we will get 0 or 1 in the beginning without even reading an input symbol. That is why I have used a dummy output symbol hash, so that we can easily ignore it while generating the output string. So now we are at the state Q0, and if the input symbol is 0, then we will reach the state Q1 so that our output will be 1. So if the input is 0, we will reach a state having output 1 so that I can get the 1's complement. Now, if the input is 1, I will reach the state Q2 having output 0. So if the input is 1, output is 0. Now, we have to complete the transitions for these two states. For the state Q1 having the output 1. Now, if I get the input symbol 0, I will remain at the same state, that is Q1, because if the input is 0, the output should be 1. And if the input is 1, then we will reach the state having output 0 to get the 1's complement. Now we will complete the transitions for this state. For the state Q2 having the output 0. If the input symbol is 1, then I will remain at the same state so that the output will be 0. If the input is 1, output should be 0. And if the input is 0, then I will reach the state having output as 1. So if the input is 0, output is 1. And that is the Moore machine to calculate the 1's complement of any binary input string. And we can verify an input string using this machine also. Let's take our input string as 0, 1, 1, 0, 0, 1. And now using this machine, we need to calculate the 1's complement of this input binary string. So we will start with the initial state, that is Q0. Now as you can see, without even reading an input symbol, I am getting the output symbol hash. So the first output symbol is hash. Now the first input symbol is 0. So I am at the state Q0 and the first input symbol is 0. After getting the first input symbol 0, I will reach the state Q1 and the output is 1. So for this 0, the output is 1. Now the second input symbol is 1. So we will follow this transition and the output is 0. Again the input symbol is 1. So we will follow this transition and the output is again 0. Now the input is 0. So we will follow this transition and the output is 1. Now the input is 0. So we will follow this transition and the output is 1. Now the input is 1. So we will follow this transition and the output is 0. So for the input string 011001, the output string is hash 100110. And this part is the 1's complement of this input string. This hash is the dummy output symbol that we have got without even reading an input symbol. So we will ignore this hash. Now, if I have used 0 or 1 in place of this hash, then here I would get 0 or 1, and that will make the 1's complement incorrect. That is why I have used the dummy output symbol hash in the initial state. So I hope this problem is now clear to you. Let's proceed to the third problem. Construct a Moore machine to count the occurrences of ABB in any input string. That means you are required to construct a Moore machine to count the number of times ABB is present in our input string. Now, how do we count the number of occurrences of ABB in our input string? By generating an output symbol. So whenever we will get ABB in our input string, let's denote it with output symbol 1. Otherwise, the output symbol will be 0. So the number of occurrences of ABB in our input string will be equal to the number of occurrences of 1 in our output string. So in this way, we can count the number of ABB in our input string. So we will start by constructing the DFA for accepting the strings ending with ABB. So our initial state is A and the simplest possible string is ABB because ABB itself ends with ABB. So the first symbol is A, second symbol is B and the third symbol is B, and we will reach the final state D. Now we have to complete the transitions for all the states. For the state A, it has the transition for input symbol A, but it doesn't have a transition for input symbol B. Now I will simply create a self loop of B over the state A. Because if the string is ending with A, B, B, it doesn't matter how many B's come before it. So we can have any number of B's before A, B, B. Now for the state B, it has a transition for B, but it doesn't have a transition for A. So I will simply create a self loop of A over the state B so that my string ends with A, B, B. Now let's talk about the state C. It has a transition for B, but it doesn't have a transition for input symbol A. Now, when I will get the input symbol A, after getting A, B, I need to go back to the state B so that after getting A, I will get B, B, and my string ends with A, B, B. Now let's talk about the state D. It doesn't have transitions for input symbol A as well as for input symbol B. Now, I'm getting the string A, B, B. And after getting A, B, B, if I get A, then I will go back to the state B so that my string ends with A, B, B. But if I get the input symbol B, it will destroy the whole pattern. So I will go back to the initial state so that my string ends with A, B, B. And this is the required DFA for accepting the strings having A, B, B in the end. Now we have to convert this DFA into its corresponding Moore machine to count the occurrences of A, B, B. So obviously in Moore machine, there will not be any final state. So we will remove this final state. Now, we need to count the occurrences of A, B, B. So whenever A, B, B comes in our input string, we will denote it by output symbol 1. Otherwise, the output symbol will be 0. So in all the states, output symbol will be 0, but with the state D, the output symbol will be 1. Because at the state D, we are getting the sequence A, B, B. So this is the required Moore machine for the given problem. And we can verify this machine with an input string. Let's take an input string A, B, B, A, B, B. Now we will start with the initial state, that is A. Without even reading an input symbol, the output is 0. So we will write the output 0. Now the first input symbol is A. And we will get the output 0. Then we have B. For the input symbol B, the output is 0. Again we have the input symbol B. Now we have the output 1. Because we have detected the sequence A, B, B. Now the input symbol is A. So for A, we are getting the output 0. Again we have A. Again the output symbol is 0. Now we have B. Following this transition, we are getting the output symbol 0. And again we are getting B. On following this transition, we will get the output symbol 1. Again we have got 1 because we have detected the sequence A, B, B. So the number of times 1 occurs in our output string is equal to 2. There are 2 1s in our output string, which means there are 2 A, B, B in our input string. In this way, we have counted the occurrences of A, B, B by counting the number of 1s in our output string. So this was the problem number 3 in which we were required to construct the Moore machine to count the occurrences of a particular substring in any input string. Now before ending this lecture, I have one homework problem for you. Construct a Moore machine that outputs A whenever the substring 101 is detected, outputs B whenever the substring 110 is detected, and outputs C otherwise. So you have to solve this question, and once you are able to solve this question, kindly write done homework in comment section. So in this way, we are done with our topic, construction of Moore machines. So this was all from my side for this lecture. Thank you, and I'll see you in the next lecture.